this in. I hope we can. So we're going to talk about the quotient rule today, but before we do that, we're going to talk about the proof of the product rule from yesterday. And this just says, recall, if f at x is p at x times q at x, f prime does not equal p prime times q prime. It's not like the sum rule. The product of the derivative of a product is not the product of the derivatives of the parts. We saw yesterday what it is. Okay, so let's get started. P and Q are differentiable, and f at x equals p at x times q at x. So, f prime equals the limit as h approaches 0 of f at x plus, x plus h minus f at x all over h. Same thing as the previous proof. We're just getting this started. So this is q, probably start with p. P at x plus h times q at x plus h minus p at x times q at x over h. We okay? That's just that opening part that we've seen lots of times. Now this proof is different. I think I talked about this previously, that the product rule does have a part to it that isn't as obvious. Like the last few that we've seen, you can kind of just work through. Yes, you need to know a little bit about the properties of limits. Like if you've seen them once, you can kind of stumble your way through it just with some common sense, or I don't know if that's the right word, but you know what I mean? Whereas this one, you kind of, it helps at least to have advanced knowledge. It would be impressive that somebody could figure this out on their own. And you kind of have to remember what to do. Okay, so we're going to split this up. And in the middle, I am going to add something and subtract it. You've seen this before. We do this when we complete the square back in grade 10 when you started doing that. It was a technique to just change the algebra of something. It can be useful. Okay. And we're going to do it again, but we're going to actually start with the subtracting part. I'm going to put it in blue so it stands out, and it's and you have to just remember what it is. Minus p at x times q at x plus h. This is the problem, I think, here is it's not even obvious that that's what would work. It kind of probably helps to memorize it, but what we do with it is add it and subtract it. Or subtract it first, then add it. And what am I missing here? The last part, minus p at x, q at x, all over h. So this is like a magic step, I think. Where did that stuff come from? We made it up. We added it in. We're effectively adding 0, so we're fine. We're going to get away with it. And then the rest of this isn't going to be too bad. It still maybe not quite as obvious. But I split it down the middle. As long as I start with the subtracting first, I split it down the middle just like we did the last proof. So that's nice that that's common in the proofs. We okay? I know it's a lot of writing, and you have to try to follow along at the same time. Again, you don't have to write this down now. You could copy it down later if you just want to watch. The order here that you choose to do this could change. So let's do this first. Limit as h approaches 0 of p at x plus h, q at x plus h minus p at x, q at x plus h over h. So this is, this, again, the same as the last one. Maybe that's a good way of doing it to keep it consistent. That's limit property number 4 again. I don't have room on the side of my page to write the whole thing, so limit property number 4, right? And then, what can I do? Does anybody have a guess? Emma? Nice. So the limit as h approaches 0 of q at x plus h times p at x plus, whoops, did that again, x plus h minus p at x. Make sure you factor it correctly, but once you've seen this happen a few times, we know what it's supposed to factor to, so hopefully you do. But just because it's function notation, like the factoring part might be a little bit awkward. And what can I factor out of the second part? If you've done everything right, all you really have to do is common factor. Like you just look for the factor. So in this case, I can factor out a p at x. Okay? Do you see what's happening yet? I'm going to write one extra line in here. We could, for this proof and the last proof about sums, we could amalgamate some of the lines. Like I'm doing a couple of extra lines that you maybe could get away without. Okay, so this is q at x plus h times p at x plus h minus p at x over h. So what does that look like? That looks like the definition of a derivative just for p. Times, and this looks like the definition of the derivative just for q, which is what we're moving towards. That's what we want to get. And then from, I believe, limit property 5, similar to limit property 4 for summing, you look at the product, limit property of products, limit as h approaches 0 of q at x plus h times the limit as h approaches 0 of p at x plus h minus p at x times the limit as h approaches 0 limit property number 5. Whoops, that was supposed to be a star. That line is limit property number 5. It's very common right around this time where people start questioning why they took this course. What am I doing in here? This is insane. I've written x plus h more times than I could ever have thought that I would. This is kind of crazy. Don't worry, it'll pass. Well, I'm running out of page here. I think I can fit it in. So, if I sub in 0, this h goes away, and I just get q at x. And what is this? This is the derivative of p plus p at x times, what is this? the derivative of Q, and that is slightly different order from how we usually write it. But that's the rule that we learned yesterday. Whew. What do you think? All right, I'll tell you what. Let's move on. We don't have time to do the proof of the quotient rule, so we'll have to do that tomorrow. For now, for Monday, absolutely, focus on the proofs before that. Okay, so the product rule and quotient rule proofs will not be on the quiz, but any of the other ones are fair game. So you don't need to memorize that one right now. Worry about the other ones. Okay, and like I said, we'll skip the quotient rule. Oh, we better write it down though. And we'll do the proof tomorrow or something. Okay, so if f at x equals p at x over q at x, and p at x and q at x are differentiable, and q at x doesn't equal 0. You often see this because functions can be constants. Could be the constant function 0, but that wouldn't make any sense. Then, so if then f prime is p prime at x times q prime, p at x times q prime at x, what does that look like? Looks similar to the product rule. What's the difference? Subtracting instead of adding. That aligns with a lot of what we know about multiplying and dividing. Multiplying powers of the same base, you add the exponents. Dividing powers of the same base, you subtract the exponents. So that shouldn't be too much extra work to remember that, to get those mixed up. But there is another part to it. Over the bottom, all squared, which is interesting. But that's the way that it is. So derivative of the first times the second minus the first times the derivative of the second, or bottom, I should say, sorry, we usually use top and bottom. I'll say that again. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. But the top part's similar to product rule. See what I'm saying? How this all comes from the idea of slope of a tangent, which is a simple idea. But the algebra gets pretty messy. And I said this to MHF students last year, and I said this to you. One of the hardest parts about calculus is the algebra. And it's just, there's so many little formulas and so many little things, and you got to be able to work with all of it. Okay, let's try it. So these are pretty simple, so we may not really need this, but p prime is just going to be 5, and q prime is just going to be negative 2. So y prime is the derivative of the top. Is everybody okay? Am I going too fast? Got this copy down? I will wait. Okay, derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. we're going to expand the top. 5 times 9 is 45 minus 10x. And then 5x times negative 2 is negative 10x, but I've got the minus sign, so that becomes plus 10x. 7 times negative 2 is negative 14, so plus 14. (45 plus 14 is 59). So now it's just a formula. But we got to know how to differentiate all the parts, all the formulas that we've learned so far, putting them all together. It's just formula. John? The reason is similar to yesterday. We expanded the top because it was easy and it's often going to simplify nicely. So we often will. And because there's a sum. Like if you think back to grade 11 when we do the work with rational expressions, we often expand and simplify the top, and then you might refactor it to see how things simplify. The bottom's already fully factored. So it's not like I could expand it and then factor it again, expand and factor it again. I mean, if I need to expand it, I will. The reason why I did it for the top is really because of the minus sign, I guess, and it wasn't too hard. If you had some big complicated, just like yesterday, you probably wouldn't bother. But in this case, we could. And so often that's the way it would work out. And then it might, like I said, simplify further. Who knows what will happen. But if something is already kind of in a simple form, like a factored form, then we would usually just leave it alone. Because often what we're going to do is we're going to solve these for like equal to 0 or something like that. And in that case, we need the bottom to be factored anyway. Or actually, we don't care much about the bottom. But okay, let's try another one. So what are we going to do first here? We're going to expand the bottom. All right, let's take a look at, let's get this one done. So if I didn't simplify the bottom, I would have to use the product rule on the bottom. Now the derivatives would be simple, so it wouldn't be too hard, but it would be more complicated. So it's way easier. This is what I was saying. When I analyze a question like this and I look at it, the denominator, I want to expand and simplify that for sure, right? Okay, f prime at t is the derivative of the top, 2t minus 4, times the bottom, 7t minus t squared, minus, what's going on here? The top, which is t squared minus 4t. All of a sudden, my pen stopped working, and it's going to be really messy, so I hope you can follow along. Oh, there we go. Whoa, that was strange. Times the derivative of the bottom.
This is the end of the lockdown drill. Thank you for your cooperation.
All over the bottom squared. So again, you might expand this part. We probably don't really have time, but oh well, we'll try anyway. Yeah, you're right. I'm missing part of it, aren't I? Thank you. 7 minus 2t. So I've got it's doing it again. 14t. How can I simplify this? Oh, this is going to be nasty. 14t squared minus 2t cubed minus 28t minus 4t squared minus 7t squared minus 2t cubed t plus 8t squared plus 7 minus 2t. I'm going to let you finish that step. But it is going to simplify a little bit further. Same as last time. Now this one, I don't know. It's quite a bit nastier because of the expanding with extra terms, but it will simplify. Okay, I want to get to one more example. We only have 4 minutes. So we're going to miss a couple. I'll put the finished version of this up online. I'm going to skip that one. Go to this one because there's a couple questions in the practice. So if we don't get all the way through this and you're confused with the practice, we could talk about it again more tomorrow, and you could do it over the weekend. Find the points on the curve y equals such and such where the tangent line is horizontal. Turns out this is a big idea. What does it mean when a tangent line is horizontal? Its slope is 0, which means the derivative will be 0. It's a constant. Yeah, what else? It means a turning point, right? That's where the slope of the tangent will be a horizontal line will be 0. And turning points are important parts of functions. So if I can find all the places where the slope is 0, or the slope of the tangent line is horizontal, the slope of the tangent line is 0, I can find turning points. So this is a powerful, powerful idea. This is going to be a big part of the calculus and doing this stuff. Okay, so let's do this. The derivative of the top, which is just 1 times the bottom, minus the top times the derivative of the bottom over the bottom squared. So I absolutely want to expand and simplify this because I'm going to work with it. So this is the derivative function. So it's the function that finds slopes. So how do I find where the tangent line is horizontal? What would I do? This is something we're going to do a lot of. So it's something you want to have clear in your head. Very nice. So we're going to set f prime equal to 0. Therefore, negative 2x cubed minus 16 over x cubed minus 16 all squared equals 0. And if a quotient equals 0, what do I do? It just means the top is 0. Right? The bottom's not 0. That's an asymptote. This is a lot like MHF. And there's 2 ways that you could do this. You could factor this. So I could factor out a negative 2. And the negative 2 is gone. And I could factor that as a sum of cubes, or I could solve it because there's only one x term. I could actually solve it like this. And x is negative 2. I'm going to sub that back in. And I'm just going to do this quickly. It works out to 1 over 12. Therefore, at the point negative 2 and 1 over 12, the tangent line is horizontal.